Hey guys, Andy Robertson here with CQE Academy, and I am so excited to share another video with you this week. And this week's topic is another one of those new concepts in the CQE body of knowledge, which is all about OEE. In fact, this lecture comes to us from my course, the CQE Masterclass, and I want to share it directly with you to help you prepare for the CQE exam. By the way, if you are preparing for that new version of the body of knowledge, stick around to the very end. I want to share a free practice exam and a free resource to help you calculate OEE in your own facility. So definitely check that out if you're interested, and let's head over to the computer and get started. All right, let's go ahead and get started. So I wanted to shoot this lecture because in October of 2022, this year, the CQE body of knowledge is going to change, and a few new topics will be added to the body of knowledge. One of those topics here in the Lean Tools section is overall equipment effectiveness. So I wanted to shoot this extra lecture to cover this new topic. The other topic, by the way, that's being added to the body of knowledge is 5 Whys. That is already included in the course as a bonus lecture with 8D and 5 Why. And of course, in October of 2022, that'll become a regular lecture where you learn all about 5 Whys, but check that out as well. Today, though, is all about overall equipment effectiveness. I wanted to start, though, by helping bridge the gap between this idea of lean tools and TPM and quality and OEE. I want to make sure you understand why we're here in the lean tools section talking about overall equipment effectiveness, or OEE. And then I actually want to go through OEE. I want to talk through the calculation itself. It is a calculation, and there's 3 attributes that make up the calculation: availability, performance, and yield. So we'll talk again about the calculation itself. And then I want to spend at the end, I want to do 2 things. First of all, I want to remind you why OEE matters. So we're going to talk about it here at the beginning, where I make the connection between TPM and OEE and quality, right? Because I do think they're fundamentally related. And then I want to come back to that at the very end. I also want to spend some time at the very end talking about how you can set up data collection to track OEE over time, and then how you can use that OEE data to identify opportunities for improvement to both improve the OEE of your equipment as well as the quality of your equipment. Okay, let's jump into this. In the world of lean, there's this idea or this concept called total productive maintenance. Okay, and TPM, total productive maintenance, is a lean tool that's intended to maximize the effectiveness of your production equipment. Now, when we say production equipment, what I really want you to think about are 2 types of equipment. So in my mind, I categorize all equipment into 3 buckets: manual assembly or manual production, semi-automated production equipment, and fully automated production equipment. When we talk about TPM, maintenance and maintenance activities and OEE in general, what we're talking about is fully automated or semi-automated equipment. This idea of TPM and OEE doesn't really apply to manual assemblies. If you do use a manual assembly, there is a concept called OLE, or overall labor efficiency, but that is definitely outside the scope of the body of knowledge. So throughout today's lecture, when you think about OEE and you think about TPM, think about semi-automated or fully automated equipment, because that's really what it's all about. The other thing I want you to think about as it relates to TPM and OEE is the idea of predictive and preventive maintenance. In the world of TPM, we're looking to improve the effectiveness of our production equipment by doing more predictive or preventive maintenance. Now, the question that most people usually ask at this point in the lecture is, well, Andy, how do you even measure the effectiveness of your production equipment? And the answer is OEE. We developed, or the tool of OEE was developed to measure. We want to create a quantifiable metric around the effectiveness of your production equipment. Now, to me, when I think of effectiveness, you can change this out to the quality of your production equipment. If your equipment is high quality, it will also be effective. Now, I also want to make sure you understand how this idea of TPM and OEE relates back to you as a quality engineer. And I want to make it all about, or I want to talk about the 2 most important attributes that we as quality engineers care about in a process. The first one is process stability. A well-running process should only experience common cause variation, and we should identify special cause variation, and we should eliminate it when it occurs. And so later on in the lecture, when we talk about data collection and how do we use data collection to improve OEE, I'll also talk about how we use that same data to improve the stability of our process. The same data that we calculate or that we use to calculate OEE can also be used to identify opportunities for improvement to improve the stability of our process. Now, the other attribute of a process that we as quality engineers care about is capability. We want a consistent process that is the same every single day and produces product that meets the customer's needs. And the argument I'm trying to make here is that if you can improve the OEE of your equipment through better predictive maintenance and better preventive maintenance and just general care and oversight from engineering and operations and all the teams involved, not only will you improve the OEE of your equipment, but you'll also end up with a process that is more stable and more capable over time. And that's why I love this idea of OEE, because I think it's really beneficial for everybody involved. Now, I've mentioned OEE a few times, but I haven't really explained what it is or how you calculate it. So this part you already know. OEE, or overall equipment effectiveness, is a lean metric that reflects the health, and of course the way I define health is the effectiveness or the quality of your production equipment. Now, OEE specifically is a calculation. So I want to give you this little acronym to help you remember how to calculate OEE. When you think about OEE or when you're calculating it, remember the acronym PAY, right? I want you to think about money, because ultimately OEE and even quality ultimately boils down to money. So remember the acronym PAY, because that's exactly how we calculate OEE. And in that acronym, P stands for performance. When we're talking about equipment, one of the things we have to ask ourselves is the machine performing at the right speed? We design equipment to run at a certain rate to meet our customers' demand. And one of the attributes of the health of a piece of equipment is making sure that it's running at the right speed. If your equipment is running slow, that could be an indication of a problem, not just that hurts your capacity or hurts your output, but also hurts the stability of your process and the capability of your process. The other attribute of an effective or high quality piece of equipment is that the machine or the equipment is available when you need it. Right? And so that's the second attribute of OEE is availability. Is the machine available to produce parts when you need it? And then the third aspect of an effective or high quality piece of equipment is yield, right? That's the Y. Y stands for yield. And essentially the question is the machine producing good parts? You know, you could have a machine that is always available and always running at the right speed, but unless it's producing parts that meet your customer's needs, the equipment is essentially useless. And so it's really important that we factor in yield into the OEE calculation, because ultimately at the end of the day, we only want to produce good parts. Now, I do want to go through all three of these attributes of OEE with you just to show you how the calculation works. And I want to start with availability. So let's go ahead and get into this. So remember, availability answers the question, is the machine available to produce parts? Now, oftentimes in the world of OEE, we talk about something called availability loss, right? So we expect the machine to always be available. Sometimes we lose capacity or we lose output due to the machine not being available. This is called availability loss. And it's essentially what it does is this availability value reflects the losses that occur due to equipment failures or setups or changeovers or adjustments. Let me show you how to make this calculation. Let's say you work at a production facility and every day your team, the team who comes in, works a 12-hour shift. Okay, this is the potential available time, right? This is the amount of time you've decided you're going to work in a given shift to meet your customer's needs. Now, throughout the shift, you're going to have what's called planned downtime. So let's say you're using a semi-automated piece of equipment and there's a machine operator who runs that equipment. That machine operator has to go on breaks, and he or she has to go to lunch. And so over the course of a 12-hour shift, you really only plan to run the machine for 11 hours because you have 1 hour of planned downtime. Now, a key attribute of planned downtime is that it should be removed from the OEE calculation. Now, once you remove that 1 hour, what you're really left with is the planned runtime or the planned available time of 11 hours. So in a 12-hour shift, when you subtract breaks and lunches, you're going to run the equipment for 11 hours. Now, during the course of that 11 hours, sometimes things happen. This is called unplanned downtime. Maybe the equipment breaks, maybe you have to do a material changeover or a setup or an adjustment or some sort of tooling change. And because of those issues, right, because of those stoppages, you lose an hour and you produce, the machine actually only runs for 10 hours. You wanted it to be available for 11 hours, but unfortunately, the equipment was unavailable for 1 hour, and so the actual runtime, or the actual operating time, was only 10 hours in this particular shift. And now that we have all these different kind of definitions in place, we can calculate the availability of this piece of equipment on this particular shift. And so the availability calculation is pretty simple. So availability is equal to the actual runtime divided by the planned runtime. So in this particular example, the actual runtime was 10 hours, right? We had 1 hour downtime, and we only ran the equipment actually for 10 hours. Now the planned runtime was 11 hours. So the availability on this particular day or throughout this particular shift was 91% of the time. The machine was available to us 91% of the time. That is how you calculate availability. Now that we have availability and we have runtime, we can look at the performance of the equipment. Now remember, when we're estimating or calculating performance, what we're really asking ourselves is the machine performing at the right speed? Now, in the world of OEE, we talk about performance loss, right? And these are any losses due to minor stoppages, right? 30 seconds here, 20 seconds there, maybe 60 seconds, minor stoppages throughout the day, and slower speeds. So let's say the machine was designed to run at a certain pace, but it runs a little bit slow. That's a performance loss. Now, I want to kind of walk you through this example. So we ran the equipment for 10 hours, right? If you think back to the previous example, we ran the equipment for 10 hours. And let's say when we designed this piece of equipment, right, you can see it up here, the cycle time, the designed cycle time was 3 seconds per part, meaning that every 3 seconds, another part is rolling off the piece of equipment, which means that we should be producing 20 parts per minute. Now, if you take that and you multiply by 60, right, what that means is every hour, you should be producing 1,200 parts per hour, okay? Do you see what I did there? 3 seconds per part, 20 parts per minute. We multiply that by 60. Every hour, we should be producing 1,200 parts. Now, if you told me you ran the machine for 10 hours, how many parts should you have produced? That's your daily theoretical maximum. In theory, if the machine ran at full speed for 10 hours, we should have produced 12,000 parts in that given shift, right? That's how much parts we should have produced in 10 hours. Now, at the end of the day, the operations team sends out an email and says, hey, today we produced 11,000 parts. And I've added a little graphic over here to say, okay, if we ran it at full speed, we should have produced 12,000 parts, but in actuality, we only produced 11,000 parts. And that difference of 1,000 parts is called performance loss. And now that we have these numbers in hand, we can calculate the performance of our equipment, right? And so the way we calculate this, performance is equal to your actual output, which in this example is 11,000, divided by the theoretical output. If the machine was running at full speed, we should have been able to produce 12,000 units in the 10 hours that were available to us. And so essentially we can do this calculation. 11 divided by 12 is 92%. Essentially, the machine ran at 92% of full speed, right? Or we had some sort of minor stoppages. But ultimately, at the end of the day, what you can see is we had some bit of performance loss throughout the shift. Now, that's not the last attribute here of OEE. The last one we need to talk about is yield, right? And yield helps us answer the question, is the machine producing good parts, okay? And oftentimes, again, in OEE, we talk about something called yield loss, and that reflects any losses due to poor quality. So again, I want to help you kind of visualize this. We should have produced 12,000 parts. We actually only produced 11,000 total parts. Now remember, when I say total parts, I mean good parts plus bad parts, right? That's 11,000 total parts. Some of these parts are good, some of them are bad. And in that same, communication from the operations team, what they tell us is of those 11,000 parts, 10,000 of them were actually good. The other 1,000 were scrap. And I've updated this picture to kind of, again, to show what we mean when we say yield loss. So of these 11,000 parts, 1,000 of them were lost to poor quality or to yield, and what remained was 10,000 good parts. And now we can calculate the yield of this piece of equipment on this given day. So yield is equal to the good parts divided by the total parts. So in this example, we had 10,000 good parts divided by 11,000 good parts. which means that our yield for this particular day was 91%. Okay, 91%. And now that we have all those three attributes, performance, availability, and yield, we can calculate the OEE for this equipment. And as we do that, I want to show you this overall graphic to again communicate how OEE losses tend to stack up. So we started with a 12-hour shift, and then we set aside an hour for planned downtime. So we should have run the equipment for 11 hours. But because we had some availability loss due to a breakdown or a changeover or a stoppage, we actually only ran the machine for 10 hours, and we lost 1 hour of productivity to availability. Then, in the 10 hours that we did run the machine, we had a bit of performance loss. So in those 10 hours, we should have produced 12,000 parts, but in reality, we only produced 11,000 parts because we had some bit of performance loss. Okay, we had some bit of performance loss. And then we also tacked on a bit of quality loss. So we produced 11,000 parts, but not all of those were good parts. Of those 11,000 total parts, only 10,000 of them were good parts. And so you can see how these OEE losses are definitely additive, and they all hurt you in different ways. Now, here's that calculation for OEE. Remember the acronym PAY: performance, availability, and yield. And what we can do here is we can essentially complete this calculation. Our performance for this particular day was 91%, availability was 92%, and yield was 91%. So if we multiply all those three things together, the overall OEE for this particular piece of equipment on this particular day was 76%. Now, I want to talk for a second about why OEE matters. So I've kind of already mentioned this, and I want to talk a little bit about what you should target as your OEE. So, we calculate 76% as the OEE, and the question you might ask yourself is that good? Is that bad? Where should we be in terms of OEE? World-class OEE, this is kind of what I've always heard, is 85%. Okay, so let's say you're down here and your equipment, regularly runs at about a 76% OEE. Your average output is around 10,000 good parts a day. And if you were to go through the continuous improvement activities to improve OEE and get it up to, let's say, that world-class number, you could increase your output from 10,000 to 11,220. Now, obviously, the number one benefit of improving your OEE is more capacity. You can essentially complete more work orders in a given shift when you improve your OEE. That also allows you to shorten your lead time. If you can build more units per day, you can complete more work orders in a day, and you can shorten the average lead time of your production process. The other thing that OEE can do is it can reduce overtime. Let's say that the piece of equipment you're focused on is the bottleneck of your production. If you increase production from 10,000 to 11,000 parts per shift, you could substantially reduce the overtime required to meet the customer's needs. The other thing that OEE can do for you is it can free up more time for preventive and predictive maintenance. If you're able to hit your production target, let's say your production target is 10,500, okay? But you've been able to increase OEE to 11,200. You now essentially have more capacity than you need to hit your daily demand. And that allows you to stop the equipment when necessary to do things like preventive maintenance and keep the equipment running in its optimal state. Now, the other thing that all that work does, right, is what it creates is a stable, capable process. When you go through the activity of eliminating downtime or going through the root cause analysis of addressing faults or addressing issues or improving yield, what you're really doing is you're improving the stability and the capability of your process. And let me give you an example. So this is how we used to track OEE. I've seen this done like this. And this is a really simple Excel spreadsheet. We've got every single day, right? We produced every day of the week. And what we tracked was breakdowns, changeovers, minor stoppages, and quality losses. And so every day the production team would come in here and they'd put in how much they produced and then how much downtime that they lost to specific machine failures, right? So machine failure A, failure B, failure C. Here were some of our common material changeovers and line clearances. And then we even had minor stoppages. So little faults on the production equipment that we could, just hit the reset button on or acknowledge and just keep running. Let me show you how this information or this OEE data can be used to improve process stability and process capability. So let's say you collect this data for a week, right? The 1st through the 7th. You've collected this data and you look at your breakdowns
And what you realize is that every single day, you're losing 30 to 45 minutes for a particular failure mode on that equipment. And collectively, over the course of a week, you lost 270 minutes to this particular failure. When you sit down as a team and you review this with your engineering friends and the people in operations and the maintenance team, and of course, you're in quality, you can go, hey, we need to do a little bit of root cause analysis and continuous improvement. What is the root cause of this failure, and how do we improve the equipment to eliminate all of this downtime? And when you eliminate failure modes from your equipment, what you're inherently doing is you're making that equipment more stable. It's more consistent over time. You're addressing problems and issues on the equipment, and you're making it more stable. Same thing with like line clearances. You're doing changeovers and line clearances. Tracking all this information will identify great opportunities. Hey, we're spending 30 minutes a day on line clearance. Do we have the standard work in place? Have we trained everybody to make sure that we're doing line clearances properly? We're doing them consistently, and we're doing them the same every single way. Are we doing line clearances the right way? The other thing that you can do with OEE data is identify trends and react preventively. So let's say you're looking at this data and you look at fault D here. On day 1, we lost a minute. Day 2, we lost 3 minutes and 4 minutes and 8 minutes and 15 minutes. All of a sudden, we're losing almost 30 minutes a day to this one particular fault. That should be an indication to maintenance or engineering to step in, initiate that root cause analysis process before we have a breakdown to identify what's causing these faults and then address the root cause of that particular problem. And by doing that ongoing root cause analysis of the problems that are identified, what you're inherently doing is improving the stability of your process over time. The other thing is quality loss. Let's say you're tracking defects over time and you notice that you have one particular failure mode, we'll call it defect B, that routinely gives you 300 to 400 defects per day, right? Which is a substantial percentage. You should engage in the DMAIC process, the plan, do, check, act process, the root cause analysis process to identify what's causing that scrap and then eliminating those problems or eliminating those root causes from your production equipment. And that, again, inherently makes your production equipment more capable of meeting the customer's needs. And so, again, that to me is how OEE goes hand in hand with quality and helps you increase your capacity, but also improve the effectiveness and the overall quality of your equipment. All right, that is it for OEE. Like I mentioned earlier, if you want to learn more about OEE or you want to calculate OEE for your own production equipment, head over to cqeacademy.com/OEE. I'm going to give you an Excel spreadsheet that you can use to benchmark off of to start collecting data today and calculate your OEE. I'm also going to give you a free practice exam to help you test your knowledge of OEE. If you're trying to roll OEE out in your facility, you can use this practice exam to help challenge your students, your learners, to make sure they truly understand it. And of course, if you're preparing for the CQ exam or the green belt exam or even the black belt exam, all of these practice exam questions will help you prepare for that exam and be absolutely ready on exam day. And the other resource I absolutely love to talk about is my free course, the top 10 topics on the CQ exam. Head over to cqeacademy.com/free course. We cover all sorts of topics: the normal distribution, control charts, acceptance sampling, reliability, ways to 7 management planning tools. All of these topics are going to be heavily covered on the CQ exam, so definitely check that out. It's got video lectures, practice exams, and downloadable stuff. By the way, if you like this video, do me a favor and hit that like button. That way other quality engineers and continuous improvement professionals just like you can find the same content. And if you want to stay on this journey to become a CQE, hit that subscribe button. That way as I publish new content, you get notified and you can stay on that journey and continue learning and continue growing. All right, thanks so much. Bye.